Have you ever looked up at the night sky and just wondered, how in the world do we see galaxies that are millions of light years away? I mean, it seems completely impossible, right? Well, today we're going to unlock this secret. We're talking about the physics of the telescope, how we literally bend starlight to touch the cosmos with our own eyes. I mean, that's the fundamental question, isn't it? The light from these super distant objects is ancient, and it's incredibly, incredibly faint by the time it gets to us. So, how on earth do we actually capture those little whispers from the past? And there's your answer. It's that simple and that profound. It's basically a two-step process. See, we can't just see starlight, we have to capture it first, and then we have to bend it. And that right there is the magic behind every telescope. Okay, so let's start with a basic problem. The light coming from a distant star or galaxy has traveled so far that it's unbelievably faint once it reaches Earth. Our own eyes, our pupils, they're just way too small to gather enough of that light to make sense of it. It's kind of like trying to hear a whisper in the middle of a hurricane. So to get around this, astronomers came up with this brilliant analogy. They think of a telescope as a light bucket. Just imagine you're out in the rain trying to collect water. You could use a tiny little thimble and you'd barely get anything. Or you could use a giant bucket. Well, the telescope is our giant bucket, designed to catch as many of those precious photons of light as it possibly can. So, how do we get started? Where does this journey of light begin? It all kicks off with one absolutely crucial piece of glass right at the very front of the telescope. And that piece of glass is called the objective lens. The first thing you need is a lens with a really long focal length. That's just the distance it takes for the lens to bring light rays to a single point of focus. You point it at what you want to see, and that lens gets to work, bending all that incoming light. You could even use a little screen inside to find the exact spot where all that light comes together to form a perfectly sharp image. Now, what's really important to get here is that this first lens isn't for making things look bigger. Not yet. Its one and only job is to be that light bucket we talked about. It gathers as much faint light as it can to create a tiny but real image inside the body of the telescope. But hold on a second. Let's think about that image. We've captured the light, which is awesome. But what does that first little image inside the telescope actually look like? What are its characteristics before we do anything else with it? So check this out. The first image is real, which is a physics term that means you could actually project it onto a screen. But here's the weird part. It's also inverted, as in completely upside down. And it's reduced, meaning it's smaller. This is the raw material, the raw data that our telescope has captured for us. Okay, so we've done it. We've gathered starlight into a tiny, real, upside-down picture inside our telescope tube. That's a huge first step, but it's not very useful for actually seeing anything yet, is it? Now comes part two. We need to make it big. And that brings us to the second hero of our story. And that is the eyepiece. It's another lens, but this one's different. It has a much shorter focal length. In this example, about 100 millimeters. You can basically think of it as a super powerful precision-engineered magnifying glass. Its entire job is to take that tiny little image from the objective lens and just blow it up so our eye can see all the detail. Now, where you put these two lenses is everything. For a basic telescope like this, the perfect distance between them is, get this, just the focal length of the first one plus the focal length of the second one. It's such a beautifully simple piece of physics. So if we use the numbers from our example, we just take the 200 millimeters from our objective lens and add the 100 millimeters from our eyepiece. And, yep, that gives us a total distance of 300 millimeters. So this incredibly powerful tool is only about 30 centimeters long. That's about the length of a standard school ruler. It's amazing, right? All that power to see across the cosmos is packed into this tiny, manageable space. All right, the stage is set. We've gathered the light with our objective lens. Our magnifying eyepiece is in the perfect position. So what happens when we take away that internal screen and we actually look through it with our own eye? This is the moment of truth. And boom, look at that transformation. What was maybe a faint, blurry dot of light to your naked eye, if you could even see it at all, is suddenly a sharp, clear, and totally enlarged image. And this is why it matters. A leap just like this is what let Galileo see that Jupiter had its own moons, which was proof that not everything revolved around the Earth. It completely changed our place in the universe. And of course, there's that one final, really satisfying step. You make those tiny little adjustments, moving the eyepiece back and forth just a little bit until everything just snaps into perfect, crisp focus. That's the moment when the image really comes alive. But you might be wondering, okay, how much bigger does it get? Well, it's not magic, it's just more simple math. The magnification is just the objective's focal length divided by the eyepiece's focal length. So for us, that's 200 divided by 100, which gives us a magnification of 2 times. Now, 2x might not sound like a lot, but that little bit of power can be the difference between seeing a star and seeing the rings of Saturn.
Okay, let's bring it all home. Let's boil this entire amazing process down. What is the fundamental 2-step secret that unlocks the entire universe for us?
It really is this simple. Step 1, the big objective lens acts as your light bucket to gather all that faint light and create a tiny, real image inside. Step 2, the smaller eyepiece lens acts as your magnifier, blowing that image up so you can see it in all its glory. Gather, then magnify. That is the secret sauce of a refractant telescope. So there you have it. With just 2 simple pieces of glass, we've figured out how to bend light from the farthest reaches of the cosmos. This simple idea completely revolutionized how we see the universe. So now that you know the secret, what will you discover next?